So, it's a new week and a new chapter. And the chapter that we're on is actually, I guess, new week, new 2 chapters or something. New first half of the book. Because what we're covering is actually old stuff today. For those of you who took mechatronics, which is virtually all of you. It's time to go back, and I promised back in mechatronics that we would learn how to use the same modeling techniques, the linear graph modeling techniques, where we found the state space models, for systems other than electrical and mechanical and electromechanical systems. And now I'm going to deliver on that promise, but I thought it would be nice to spend a day to review what we did and how we did it back in mechatronics. So that's today. We're going to go back, we're going to remind ourselves how to do this electronic and mechanical and electromechanical system modeling techniques. And then the rest of the week we're going to do fluid and thermal systems. Okay? And we'll see how today goes. We might get into the next lecture today if things go quite smoothly. You guys know that I like to keep us at a good pace so that we can get through all the material so you guys end up being well-rounded engineers.
I think so.
Okay. So, a quick review. Most systems of engineering interest are very complex. In fact, too complex to compute if we want to be completely precise, because you get down to the quantum level and you can't really compute all of those things unless you have a computer that is unimaginable today. Okay? So, we can't do it. However, many of these systems can be lumped into several parameters which can be mathematically described and still represent most of the interesting behavior of the system. So for us, that lumping is actually pretty significant lumping. We say, oh, all of this stuff, well, it's kind of like a mass, kind of like a spring, kind of like a damper, or whatever. Or it's kind of like a resistance, electrical resistance. For electrical systems, it's actually a little bit more discrete in how those systems are composed typically. So there are many important electrical components that have lumped parameter models. The 3 most important to me are listed below, along with their elemental equations, in terms of the electrical power flow variables voltage, V, and current I. Okay, so resistor has an elemental equation. Do you guys remember? Yeah, so VR equals IR times R. So Ohm's law, right? And then the capacitor has dVc dt equals
1 over C.
1 over CIC. Good. And then the inductor,
IL
DIL dt equals
1 over L VL.
Yep. 1 over L VL. Good. So that's familiar to most of us at least. And we are sort of waking up some neurons here. When we do modeling of these electronic systems, what we do is we write down the elemental equation for each of the components in the circuit, right? And then the other information that comes in comes from the compatibility and continuity equations, which are essentially just Kirchhoff's voltage and current laws. but we like to choose very specific ones to write down, right? We didn't just write down, because you can write down a lot of KVL loop laws, you could write down a lot of current node laws, right? But we wrote down just the equations we needed to solve. Remember, we learned that technique of just writing down the minimum number of equations and hopefully solving things without too much algebra. Sometimes it got messy. So let's analyze an RC circuit as a refresher. Okay, so this is our good old friend, the RC circuit, with a voltage source. And we're gonna, mix it up a little bit today. We're gonna find the transfer function because we just learned how to find transfer functions. So why not? Let's find the transfer function from the input Vs to the output Vc. So from Vs to Vc. And we are going to use the technique that we're going to develop the whole state space model and then use that last result that we found last week to apply to this problem to find the matrix transfer operator and the matrix transfer function. However, this is a single input, single output system, isn't it? And so what is the dimensionality of the matrix transfer function? What? This is actually the order of the system doesn't matter for how many dimensions the matrix transfer function has, because matrix transfer function dimensionality is just number of outputs by number of inputs.
So 1 by 1.
So it's a 1 by 1. So it's the matrix transfer operator here is just a scalar. But we can still use the formula. It still works. It's just kind of trivial. So, all right, let's do this example then. So find the transfer function. So what is our first step typically is to draw the linear graph and normal tree, right? It's really easy for circuits. So we draw a ground node to be here. We'll put in our voltage source, and we have to make sure that we draw the source with the arrow. Since it's a cross variable source, the arrow goes towards ground if that is the way that this plus minus drop is on the diagram, and it is towards ground. So there's our Vs. Then we have this just one loop, right? It just goes through R and then through C back to ground. So we could go through R, through C, back to ground. And we could draw arrows that way, although we know that this is just a sign convention to go away from sources and towards ground. But it's helpful nonetheless. So R and C are represented there. And our normal tree is the next step. Do you guys remember how we determine what the normal tree is?
The root variable primary sources and the cross variable secondary source.
I think you're thinking about how we find the state variables, which that's the next step. So, but we're just getting a little ahead of ourselves. Let's just find the normal tree, which is the first thing we always find is this cross variable sources. Right? That's our top priority. And remember that we're going to select until we can't select any more without creating a loop. So top priority is cross variable sources. Second priority, it's the A-type energy storage elements. Right? So which is a capacitor in the electronics case. And then we can't select any more, otherwise we create a loop. Yeah.
Can you read that question from the beginning where it was like the order of the transfer function? Is that how you worded it? Like it's out over in and it gives you the...
Yeah, I think I said it correctly. The dimensionality of the matrix transfer function is the number of outputs by the number of inputs. And I'm thinking of, I think the way that I usually think about it is that y equals h of s times u. And so the number of outputs has to be the first dimension, and the number of inputs has to be the second dimension, because it has to match up with the u, which is the input. That's how I think of it.
Okay.
So, yeah, it's m by r in the symbols we typically use, m by r. M is the number of outputs, r is the number of inputs. I remember, it's in the notes that I wrote up on that, so you can refer to those for specifics.
I want to make
And-
sure I had the question down right.
Yeah, better memory. I always look at my notes because my memory tends to like blur things a little bit. It's like, I think this is right, but I'm pretty confident this is because of this equation. So, I turned this blue. So this is our normal tree, which helps us to find the variables, so the state variables, the primary, secondary variables. Let's write up here, let's write the primary variables just for fun. Do you remember what they are? They're across variables on the elements that are in the normal tree, and they are through variables on elements that are not in the normal tree. So it's VS, comma, VC, comma, IR. Good. And then our secondary variables, secondary. Sometimes in these simple problems we skip right to state variables, but we'll go through this because we haven't done it in a while. So secondary variables are what? I, C, and VR. It's just, you just flip all of these bits. And you get okay. Good. So the state variables are a subset of the primary variables, right? And it's across variables on A-type energy storage elements in the normal tree. Just rolls off the tongue. And through variables on T-type energy storage elements not in the normal tree or in the links. Yeah, just smooth right off the tongue. So in this case, we only have one energy storage element, and it happens to be in the normal tree, right? Conveniently, it's VC. So what would the state vector be if we were to write it? Just VC. And the system order, then, first order, very good, n equals 1. Awesome. So our elemental equations are first. Isn't this fun? Like, we're just rehashing stuff, and like all these neurons are waking up, but it feels good because you already know it.
I like this problem.
You're just going through it again. It's like, I don't know, it just feels great to me. I enjoy it. So, elemental equations, we like to write this column of all the elements, right? All of the passive elements, the non-source elements. So the resistor and the capacitor are the only two. So what is the elemental equation for the resistor? Wait, I already did that. Didn't I do that?
Yeah, it's in the other page.
You wrote it.
Oh, I wrote it up. This wasn't part of the problem. So, okay, we just need to rewrite it here. VR equals IR times R. And then, what was the C one?
DVC.
So, these just come from above. We wrote down what the elemental equations were for those three common components. And now we get to write the continuity equations. And I'm going to copy the linear graph down just so that we have it here to look at while we write.
Don't we need to rearrange the elementals?
Do we? I don't know. Let's see. We don't need to rearrange this one. Do we need to rearrange this one?
Yes.
So we want to solve it for the secondary variable, right?
Secondary?
Oh yeah, that's something.
I thought that was a continuity and compatibility equations that we solved for secondary.
Oh yeah, no, you're right. Primary. So IR.
Remember things.
Very good. You caught me.
Testing you.
Okay, so there we are. So they're all solved for their primary variables. That is correct. The elemental equations should always be solved for the primary variables on the left-hand side. Continuity and compatibility should be solved for the secondary variables on the left-hand side. So the continuity equations are the ones that you get when you draw a contour and you sum up all of the through variables going into it, right? And I think I like to use purple for these contours. Those ones are, yeah, purple. So remember that we want to intersect with this contour one and only one of the what?
Variable branches or something?
Of the branches of the normal tree that are passive. So we need to do that for each contour. We need to do that. So this does, that contour does. Just looking at that node essentially. And you only need to do one because you have to do one for each passive element in the normal tree, which there's only one passive element in our normal tree, so we just have to do one continuity equation. And I like to skip immediately to, and I noticed towards the end of the semester, some of you guys were picking up this trick, which I like, is that you write down the through variable of the branch that you cut through that's in the normal tree, because that's the one you need to solve for anyways, because it's always going to be a secondary variable. So IC, in this case, equals, and then all of the stuff going in, because this is going out, so it has to equal all the stuff going in, which in this case is what? IR. Excellent. And now the compatibility equations, which are found by doing what?
You put in a non.
Put in a link and just make a loop.
Yeah. You put a link into the normal tree and creates a loop, because that's how you created the normal tree, is that if you put any of the links in, it would create a loop. So if you put in each of the links into the normal tree, you get a loop. In this case, there's only one link, so you just stick it in the normal tree, and you get out this loop, which I like to write, once again, I like to write VR equals, because that's the across variable here, equals, and then I start at the tail of it, and I go to the head. So I say VS minus VC. It's just like vector addition. Okay? But if you ever get like confused and don't know, how do you start at the tail, how do you do this, all you need to do is just start at any node and go around the loop, and if it's dropping in that direction, just write it positive, and if it's gaining in that direction, write it negative, and you set it equal to 0. So you don't have to worry about getting that right. Just go around the loop, make sure that you do, actually it doesn't even matter which one you do positive, which one you do negative, as long as if you're going with the arrow, you do one sign, and when you're going against the arrow, you do a different sign. That's all you need to remember, that it has to equal 0. Okay, so we have that. That's the only one we need. So algebra, state equations, it's almost just trivial. So I'm just going to, although we like to sometimes rewrite this, plug these guys in, eliminate, whatever. This is so easy that I'm just going to write it in one line. So this dvc dt, so actually it's going to be our, so dvc dt, I'll just write dvc dt just to be complete. dvc dt equals, I'll rewrite the 1 over c, and then we need to plug in for IC, right? which is just IR. So I'll plug in IR. Okay, so IR is not a state variable, and it's not an input, so we got to eliminate it with, we have, for IR, we have an elemental equation for it. It's equal to VR over R, but I'm going to put the R over here. So we have 1 over RC times VR. And VR is also not a state variable. It can be eliminated by this compatibility equation, which is Vs minus Vc. And what is Vs? What type of variable? Source, input variable. What is Vc? That's the state variable. So we're done, right? We're done. Easy. Standard form, then. We just need to write it as x dot, but I'm refraining from using the dot in this problem because it's an electronics problem. So dx dt equals, it's ax plus bu, right? But we want to write our A matrix. What is the dimensionality of our A matrix? So our
2 by 1.
x vector is a what?
1 by 1 by 1.
1 by 1, and it's just VC, right? And the x vector over here better be 1 by 1 too. So that means that a 1 by 1 is multiplied by something equal to 1 by 1. So what does it have to be? 1 by 1. 1 by 1. Plus some B matrix, which we know has to be a 1 by something, because it has to be additive with this stuff, and times the number of inputs. What is the one input? Vs. So our B matrix is a 1 by 1 as well. So what is the only term here for VC? Negative 1 over RC. Very good. Negative 1 over RC. And what is the coefficient of Vs? 1 over RC. Beautiful. Beautiful. It's just, I mean, I know this is like a simple example, but it's one we could get through pretty quickly and we're familiar with. But it goes through all of the steps, right? We're doing all of the things that we need to do. And now, oh, we need to write our output equation. That would be sad. That's like 10 points on a midterm exam. You got to write the output equation too. So Cx plus du. So our number of outputs, I said this is the transfer function we're looking for. So I defined that the output is going to be Vc, the input's going to be Vs. So there's only one output. So the C matrix has to be what by what? 1 by 1. Vc is our state vector, our state variable, plus the D matrix times Vs. What is the Vc coefficient if we want our output to be Vc? 1. Boom. What is our D matrix if we want our output to be VC? 0. Because we want 1 VC and none of the VS. And also none of the BS. Ah!
Systems jokes.
Thanks. Transfer function. Ready to do this? This is the stuff we learned, so we're going to apply it here. How do you find the transfer function if you have the state model?
What's over input?
Yes, but it's we solved for an equation that gave us, in terms of the A, B, C, D matrices, what the transfer function is. So we have our A, B, C, D matrices now. So I would recommend we just use that solution. So I'm going to write, to jog your memories, H of S equals, I'm hearing it out there.
It's like the
Yes, beautiful. And in this case, it's all trivial because everything is a 1 by 1, which can be treated as a scalar. So that's great. So our C matrix is 1 times Si minus A, which the identity matrix for a 1 by 1 is just 1, so I'll just put the S in there, minus A, which is just negative 1 over RC, inverse B, which is 1 over RC, right? Plus D, which is 0. And we can just immediately drop, when everything's a 1 by 1, we can just treat it as a totally as a scalar. And the inverse is just, so inverse of a 1 by 1 matrix is just its reciprocal, which is just what you would want it to be, because we use the same notation for the reciprocal to the minus 1, right? So we end up with the 0 has no effect. The 1 is just doing nothing to this. So it's just whatever the numerator is divided by whatever this is, which is S plus 1 over RC. And I guess I'll do it in 2 steps. I'll put the 1 over RC from here in the numerator. I know you guys like it when I do multiple steps. And then the denominator, we're going to have S plus what? One over RC. Very good. Anything else? Did I miss anything? Of course not. So, to simplify this, we can just multiply the numerator and the denominator by RC, right? And we would get 1 over RCS plus 1. And that is our answer for our transfer function. Now notice, I should write a note here, dropping the matrix notation. That's what we get. Okay, any questions on that example?
So don't you just have like dy over dx and like line things up so it's...
So do you want? What you would like, I think, is to find the scalar input-output differential equation from the transfer function.
That's the term I was trying to remember.
Yeah, let's do it. Let's do it. If we want to know what the IO-ODE is, so I can just do it like right here. We know that we have H, which is equal to this, and we know that H is equal to the output over the input, right? So if our output is y, and our input is u, and this is equal to 1 over RCS plus 1, then all you do is essentially cross multiply, and we get RCS plus 1 times y equals u times 1, right? And we can distribute the y. Wherever we see an s, we think time derivative of y, right? So s squared would be second time derivative. We only have an s here, so we're going to have r, c, and then I'm going to just cheat and use y dot because I don't have a lot of space. Plus y equals u. So that is an input-output differential equation that we could all solve. We could have solved the original state model too, because we know how to solve that now too. Find the state transition matrix, etc., etc. We would need initial conditions for either of those cases. So for now, our transfer function doesn't mean a lot to us other than it's a sort of an intermediate representation. We can go between state space and we can go to input-output ODEs back and forth. But I haven't yet shown you sort of the power of that transfer function yet, and we'll get there. So, yeah, that was that. Good question. Yeah, I like that. Mechanical translational systems are next. So we just covered electronics. Done. Moving on. Mechanical translational systems. The power flow variables are velocity and force, V and F. These variables are related in mechanical elemental equations. Here are the three most common translational lumped parameter elements with their elemental equations. So the damper has what as its elemental equation? The force through the damper is equal to BVB. And the mass, dVm dt, 1 over m Fm. And this is just Newton's law, right? The damper just says that the force through it is proportional to the velocity. That's how I remember that one too. And then the spring is just Hooke's law, but it's differentiated. So it's dFk dt equals k times what? Vk. Nice. So we do a very similar thing with these mechanical systems. Let's do a simple example. Define a lumped parameter model of a makeshift vibration isolation table made of a large stone slab resting on old tires. Because why not? This is actually not a bad way to give yourself like a sort of DIY vibration isolation table. Big, heavy slab of something on top of tires isn't bad. Draw a linear graph and normal tree. So we're not going to go through the whole thing. We're just going to do the linear graph and normal tree. So say we had some sensitive equipment on there, and we're like, okay, we don't want vibrations to get through. Let's see, we put 3 tires, and we know how much the stone slab weighs, and we know how much the equipment weighs. What kind of vibration isolation do we get is the sort of question we might ask. And so we want to model it. And that's what we'll do here. So let's draw just a diagram that's like a lumped parameter diagram of it. I feel like this stone slab and the sensitive equipment can be modeled as a mass. What do you guys think?
Yeah.
Yeah, I think so. Mass. And then we know for sure that there's this shaky ground down here, and that's probably going to be like some sort of a source, right? It could either be a force source or it could be a velocity source. Most likely, we're going to want to measure it. It's probably most easily modeled as a velocity source. We're going to measure this thing as a position, probably, that's moving. And so, yeah, it's probably most easily modeled as a velocity source. Okay. And then how do they connect? So the shaky ground is the input stuff, and then this mass is kind of like the output velocity motion. What happens in between? So I think both are in order here, right? A spring and a damper. So why a spring?
Because they have like bounce.
Yeah, so they're elastic, right? So if you compress them, they'll restore. That's something that a damper won't do. If you compress a damper, it won't restore itself to where it was. So it's spring-like, okay? But it's also damping. There's some damping in there. And why? How do we know that? How do we know that there has to be some damping there?
Put it on there to decrease the vibrations in your equipment.
Yeah, so that's one way to argue it. But also, a damper is the only element in the system that dissipates energy, right? Because the mass is an energy storage element. The spring is an energy storage element. So we know that if you were to take your sensitive equipment and hilariously just drop it on the stone slab, that it would make probably the table shake for a minute, right? But it would stop shaking. If there was just a spring there, it would just shake forever, right? It would never dissipate that energy. So energy is being dissipated somewhere. There's probably a little bit of damping that comes from the air moving around it as it moves, but probably most of it's coming through the tires just having internal heating up that happens. So it heats up as you compress it and stretch it. The tire will heat up and it'll dissipate some energy. There may also be some acoustic energy that happens, especially in the case of dropping these sets of equipment on the slab. Probably some acoustic energy would happen there. So, okay, how do we draw a linear graph of this?
We draw the ground.
Draw the ground. We always have to have ground, right? What other distinct velocities do we have in this system?
The velocity source.
The velocity source, so that's a node. And the mass velocity, that's another node, right? So the mass, so we have the source here. Draw the arrow in a moment. Or sorry, not the force, the velocity source there. And then we have the mass always going to ground, right? Mass is always referenced to ground. And we will now look at our velocity source. And do we know which direction to draw the arrow yet?
No.
No. What do we need to do?
Define it.
We need to define a positive direction, a coordinate arrow. Let's define it that way, because our velocity source is pointed that way, and we just don't want to do weird things. So let's just do it this way. If they're pointed in the same direction, we know that an across variable source always points down to ground, which is how I always remember it. So that's our convention. And so there's our VS. And then how are they connected?
Aren't they both going from the velocity source to the mass?
Yeah, so the K and the B have to go from here to here. They're not in series, though. They're in parallel, right? So one has to go this way, and the other one has to go this way. And which direction should I draw the arrows?
Towards the mass.
Towards the mass. That's our convention, is to draw them in the direction of the coordinate arrow, which is from the velocity source to the mass, from the velocity source to the mass. That's our convention. If you get those ones, arrows mixed up, NBD, it just, your signs will be opposite. You just have to interpret them the opposite way. It's just a little bit easier to interpret if you do it this way. All right, so what's our normal tree? That's the last thing we'll do on this example.
Sources.
Across variable sources. So if it's a through variable source, we wouldn't select it, but it's a cross variable source. And then, okay, so we want energy storage elements of a certain type in the normal tree. First, what is our first priority? A-type, which is associated with cross. So A-type energy storage elements are first. So K and M are both energy storage elements. The mass is an A-type. K is a T-type. So T-type is the lowest priority to go in the normal tree. The next priority would be actually transformers or gyrators, right? We don't have any of them in here. And then after that, it's D-type energy storage elements. But notice that we don't have any room for anything. If we select either of those two, we have created a loop, and it's not a normal tree anymore. So now we would be able to launch into the automatic procedure that we know and love, right? Yes. Okay. So let's round out this lecture with the discussion of mechanical rotational systems. I'm not going to do an example of these because we just don't have time. But review previous material if you would like. We'll just kind of refresh our memories as far as what types of components show up. the mechanical rotational power flow variables are omega, the angular velocity, and t, the torque. These variables are related in the mechanical elemental equations. Here are the three most common rotational lumped parameter elements with their elemental equations. The rotational damper, we know that the torque is proportional to what? The constant proportionality b is proportional to what? Omega b, the velocity, angular velocity, right? Very good. Moment of inertia is going to have what?
R squared d.
So it's d omega j dt. Whoa. dt equals
One
over
j
J.
tj.
Because this is kind of like mechanical systems, but like they're representing different things.
Yeah, so they're mechanical rotational systems, and they're very analogous. Just like in dynamics, you had the F equals ma. It's very similar to the torque equals J, omega dot, or alpha you guys probably used in dynamics class. Yes, and then finally we have dtk, dt, k omega k. Excellent. Okay. Any questions on that? That was well-timed lecture, guys. It is 11:49. We're wrapping up. I can make it to my meeting at noon without being late.
Wait, I have a question that requires some answer.
Oh, dang. Okay.